Alright. Need to do a camera check these days before I actually do all this. So, today we're doing something a little different from the usual. I'm taking a slight break from all the UI, or not the UI, the AI work that that I've been doing in the past, just because it's such a large system that honestly it's requiring me to do a lot of thinking about the structure of the game going forwards. Because AI, as I've mentioned before, is something that touches on pretty much every other subsystem in the game. It's not even just like a little like, oh, it, touches on other entities here and there. No, resources can change the entire AI states of other AI. And I want to make sure that I get this done not just in such a way that it's easy for me to design, but also so it's reliable and stable in the future. So I'm taking a little break from that today, and actually today's going to end up probably being in two parts. I'm going to have some optimization this morning. This probably, hopefully, will be somewhat short, and then I'm going to come back later, possibly today, and then end up doing a little bit more work just fleshing out features, or just doing something cool like getting waves in water working, or something like that. So the thing that I'm most kind of worried about is you'll notice, okay, I'll press enter in a couple seconds and we'll see how long it takes for it to generate a level. So 3, 2, 1. There we go. You can notice that took a long time, and even without the terrain visible, it still took quite some time to get right. Also, I kind of can't help but laugh at the fact that the water is not being hidden, even though the node perspective mask is here. Oh well. I'm actually even going to turn this off so I can continue to see my terrain. King Elizabeth, did I end up getting a job offer? I've got some offers, yes. Hopefully I will have a job by the end of the month, and if all goes well, I might even end up at GDC, which would be really nice, because that's kind of the who's who of the gaming world. It's nice to be able to hobnob with everybody there and at least network a little bit. Thank you. It's especially nice to know that my skill set is clear enough that it's valued by a fair number of people, and that even in losing my job I can still find a new one fairly quickly. And that's something that comes from not just being a game designer or a game programmer, but if you look at my skill set, it's fairly broad. I am able to do a lot of different things. There we go, there's our terrain. And because I'm very broad, I'm not exactly locked to one sequence or another when it comes to like, oh, I'm only good at network programming, oh, I'm only good at specific other things. Like, no, I can kind of jump in and do what I please and help out where I can. So yeah, you guys will notice I also have the monster cat bot. It'll be doing its thing throughout the cast. We'll see if this is an improvement or not. I've been having a lot of trouble with music getting my VODs muted. And so I figure this might be a way to avoid that. We'll see if it works. So anyway, it looks like we're at about 1 or 2 seconds of world generation time. Not the end of the world, but it's still a fair amount of time, right? 3, 2, 1. 1, 1000, 2, 1000. Like, that's a fair amount of time, and this is not a large world. I mean, look at the extents of it. I can scroll from edge to edge of our created world in a fairly short period of time. So we're going to do a little optimization just because, first off, every time I test, keep in mind that's an extra 2 seconds that's getting added to the amount of time it takes to test something. Also, the other thing to keep in mind is that not only does it add time to testing, but this is something that the moment we start to generate larger and larger maps, that's going to grow, probably. And we have to figure out why it's growing. Maybe we'll even do a little bit of math to figure out how bad it is, and then we'll figure out how to fix it. So, I have some sneaking suspicions that it's somewhere in the cell generation. I don't exactly know where, but we loop through the entire set of cells a fair number of times. Not only do we loop through to actually create them, which is fine, it's the loop through to set them up that I assume that there's some other looping going on inside. So we have like nested loops that are trashing our performance, and we need to fix that. So what I'm going to do is I'm going to bring up a program I like quite a bit called Very Sleepy. And granted, so I'm using Very Sleepy right now because it's a fairly simple program to use and contains a good basic setup of what needs to be performance checked. So specifically, we'll see, let's see, where's the engine? Refresh. There we go. So here's our engine, and you can see kind of our thread usage is pretty low right now. In fact, pretty much everything in here, it looks like it's spending most of its time in sleeps or inside message processing for Windows. Like, that's fine. This is perfect. But what we're going to worry about is the moment we go and load a level. So we're going to tell it to profile all, and I'm actually going to prep a world load so we don't have a ton of other stuff in there. So we're going to start profiling, we're going to tell the game to generate a level, and then we're going to stop profiling the moment it's done. So, ready, set, hua! There we go. And there's our call stack. Cool, let's kill the game. So, let's look at this for a bit. Wait for multiple objects is essentially it's a thread synchronization technique. Same for wait for single object. These are all, along with the sleep, and these wait for multiple messages, wait for single object. These are all things that we can throw out. This isn't something that's wrong with the game or the engine. This is actually the engine having so much spare time that it's having to call these waits so that it can synchronize all the objects. And that's fine. That's not a big problem. Our big problem, you'll notice this cell contains vertices. It says it spends almost the entirety of the 2 seconds in this function. I mean, look at this. Like, 1.56 seconds in this little bit of code. Now, this is kind of a misnomer, because if you look at this, this is a simple piece of code, right? It's not that this piece of code is getting run once and taking 2 seconds. It's that we're calling this function so many times that it's actually causing us a little bit of problem. OzPlayer, I have been coding now professionally for about 5 years. I've been coding games and game-related things, I would say, for the better part of 8 years now at this point, I think. I've been at it for a while. Okay, so the cell edge contains vertices is not our problem, but it's a symptom, right? The problem isn't in this function. It's the fact that we are calling it so many times that it's bogging us down. And you'll notice here in the called from, we can actually look at the various call stacks and who uses it. And the big thing to notice, we can see 98% of the calls come from this find edge by vertices function. Okay, so here's a loop that I worry about. For each edge in the edge list, we look through every single edge. Ugh, that's frightening. That might be causing us issues. So let's actually dig through the code. Since we know where our problem is somewhat situated, we should be able to dig through and figure out what the heck's going on. Now, the other things to notice, we have find in pointer array. Is taking up a little bit of time. Not nearly as much as this cell edge contains vertices, but it's still taking up a fair bit of time. So this might be something to investigate next as well. Everything else, though, you'll notice is so small. It really is just these 3 functions. So if we can iron these out, we actually should have a nice fast world generation. Let's see. Contains vertices. Alright, it's in here somewhere. Contains vertices. Okay. and it's getting called by find edge by vertices. Is that in here? Find edge by vertices. Well, so here's a caller. Let's see if we can find all the callers of it. Oh, sweet, there's only one person calling it. Okay. And it's inside the cell constructor. So remember, the way this stuff is working is that we are calling for each, let's see, so for each cell group we are creating, and a cell group contains a set of cells, a 2D array of cells. So we say for each cell in the cell group, create that cell. So most of this code is going to be somewhat unavoidable. And the big thing here is that really we're going to have to go through some of this, but we should be able to clean this one up at the bare minimum because it's the only user of it. You also notice here's a find in pointer array. This one also looks like it could use some cleaning up. So both of these have this loop inside a loop inside a loop problem that we need to solve. Otherwise, we're going to have trouble. Sorry, I've got a bit of a mess sitting next to my computer. I honestly should clean up. It's one of those things. I'd rather be programming than cleaning my desk, and so it's how it goes. I have a mess. Can you see the game, and what do you do in the game? For now, I'm in the middle of working on something, so I'm not going to boot up the game unless I need to. But there's a description in the stream description below of the very, very basics. I honestly need to update that with something more along the lines of like an elevator pitch, just so it's a little more succinct. So when you're optimizing, and this is something that's always true, kind of no matter where you're optimizing and what you're doing. Really? Oh, my tablet's not plugged in. That would explain why the tablet is not functioning. You see just how prepared I am for this today. But I decided optimization would be a good thing to work on. So when you have your code, you can think of your code in layers, right? We have main, or the main function that calls everything, right? And so the one function that calls everything, here's our main, or whatever, call it our entry point, right? And then from main, okay, say we have some for loop that does stuff here, and then say we have another for loop sitting here, and then we call some function. It's probably, function would be here. We call some function and hand it things, and then inside that function we do another for loop, or we do like a while loop or something. Right? Something simple. If you look at the places that you are going to be optimizing, right? If we look at each of these lines as they go down, and we can just kind of translate this into here, right? We have a while loop in here. Obviously this isn't terribly good, because each time we go in a layer further, each of these layers is happening an almost exponential number of times more. For example, if this loop happens 10 times, and then this loop happens 10 times, this loop isn't just happening 10 times, it's also happening this 10 times as well. So we end up with 100 loops right there, and then, okay, this function's going to get called that 100 times, and say this while loop happens another 10 times. Well, this while loop's going to turn into 1,000 because of the 100 we've got here. And you can see how very quickly this becomes a mess, how very easy it becomes to create a monster inside of our code. And even if we're doing something simple like int x equals y, right? Even if we're doing something as simple as a variable initialization, or let's say we're doing some simple math thing. We're saying, oh, this is the ceiling of I divided by y, right? something like this is going to, even though it's simple, right? Math is fast when you think about the things you can do on a computer. Computers are good at math. It's kind of what they were designed to do. So even something simple like this little math function here, because it's being called thousands of times, is going to be slow. Not because the math is inherently slow, but because you're calling it so many times that it's going to affect our functionality. So, what you have to do is you're going to do what's called finding the tightest loop in your program. And the tightest loop, so if we think about each of these for loops, and I'm going to swap to let's get some blue. So if we think of each of these functions as a loop that we're going to be calling, especially in something like games, where it's like, okay, main, we're going to not just call main once. Main is something we're going to loop through. And I cannot draw circles, apparently. Let's see here. Whatever. So you have the one loop, and then inside of it you have another loop, and then another loop. So this, essentially the smallest loop on the inside, the most tightly wound loop, is the one you want to optimize first before you go outwards. Because remember, whenever you optimize something, you tend to make it more difficult to use. So we want to optimize as little as we can to get the biggest effect. And so something that's getting called 1,000 times, if we can optimize this down to oh, I don't actually need it to be the ceiling of this crazy math function. If I can instead do something like, let's not do the ceiling of I over Y, let's do something a lot simpler. Let's say I get the same results from Y minus 1, or just even an X equals Y or something, right? Let's say it's Y minus 1. Suddenly this is going to go a lot faster. Your whole program will go a lot faster because your tightest loop is now optimized. Now, obviously you're going to see different amounts of performance change depending on how much you're able to optimize your tightest loop. But still, the point still stands that what we're doing here is we're trying to find the tightest loop and either call a function less or make that tightest loop faster. So for us, we have cell groups, right? And size. Why did the size change? So we have a cell group, right? That is, let's see here. And then the cell group says, okay, for each cell, right, we're going to create a new cell and then insert it into the array. So I'm just going to call ci equals new cell. And you'll notice inside each new cell that we then check for two things, right? We have a for loop in here that says from I to 4, or I from 0 to 4. Let's do this correctly. From 0, dang it. No, that's not the way to do it. Erase, Rob. There we go. So I from 0, there we go, from 0 to 4. We're saying, okay, check if we say for each vertex first, we're looping through that, and we're doing some if statement in here, and then some code after it, which we don't really care about. And then we say again, for I goes from 0 to 4, because once again, we're working with squares. Then we say for each edge, and we check for existing edges as well. And then there's some basic if statement here and some more code here. So these are the things we want to look at first. And then we're going to step back and say, okay, is there a better way to do this as well? Now, granted, we're probably not going to be able to shortcut any of the for I goes from 0 to 4, but we might be able to shortcut something in here instead. So instead of going all the way out to that for loop, we're just going to look at the for each loop and see if we can do something better. So, I'm going to actually leave that up, if only so that I can come back to it. Yeah. So, when we look at our code, or at this code in front of us, I should say, find in pointer array is one place that we need to clean up, because you can see this is a for loop inside our for loop. So it's probably something we can do faster. This is not something we can really improve, right? If the vertex doesn't exist, we always have to add a new vertex, and no matter what, we have to assign this vertex to this position in the array. Can't clean that up. There's nothing faster we can do. But this find in pointer array is one place we can go faster. So let's see here. Question is, how do we make this faster? So right now, find in pointer array does something kind of stupid. It says for each element in the array, we check if these are the same, and then we proceed to return I afterwards. And if we look at our usage here, we're handing it a vertex list of point2D pointers, so an array of point2D pointers, and then we hand it a point2D itself. So as much as I like this array helper, this array, the fact that we can't just find in the array, is something that's bothering me. So one thing I'm thinking of, and I might have to, you know what, actually, let's go for the bigger fish first. Let's actually go for this find edge by vertices, right? This is the sucker that's taken up the most time. And this does something very similar, right? It says edge in the edge list. Grab that edge. If the edge contains the vertices given, then return it. Otherwise, don't return anything. So this is an inherent problem with these array classes, is that they're great for storage. They're not so great for shared storage. So we need specifically a data structure, I think, that is going to fit this kind of storage better. So let's see what we got. I'm going to pull up some docs, see what we can do here to clean this up a little bit, because it is, as much as I like the simplicity of the arrays, we obviously need something else here. So let's see here. I'm going to pull this sucker across, get our documentation in sight. There we go. So, Thorax, wow, Thorax? Is that how I say it? I'm not using STL containers and iterators because STL does not play nice with the memory manager that is inside this game engine, because the game engine has overridden new and delete, and because it has overridden new and delete, the STL systems don't quite work well with that, because they also introduce new and delete, or they introduce their own new and delete as well. So let's see here. Array is what we're using, and right, any find function here, so there is a find element function, but you'll notice that it says the running time of this function is big O of n, which means the worst case that this function is going to run is going, when you say find element, it will look through every element in the array once. And that's our current problem, because we're doing the same thing. We are looking through every single element in this array 4 times per new cell that we create. So there's also an assumption I just realized I'm making that is not that great. But it's an assumption I want to hang on to. So right now, you'll notice that I'm calling this find edge by vertices function 4 times, regardless of where we are inside the cell. And remember, I'm creating the cell upper left to lower right every single time. So if we get smart about this, the first thing my brain tells me is that every cell, no matter what, is going to exist on the either most right hand and most bottom part of our generation. So if you think about, I'm going to pull up Paint again because this is I said it, but I don't think it's too obvious unless you, let's nuke this. There we go. So okay, imagine I've got my 2D array of cells, and as I create them, I'm creating them from right to left, top to bottom. So what's going to happen is, each time I create a cell, the two edges that I know aren't going to exist are these two, right? Because when I create this cell, okay, now I know that these previous two ones exist, like this one exists, but this right-hand one is never going to exist. And for each time I create a new cell, this right-hand one is always going to look through the entire list once. It's only on this one right here when we have an edge case that we need to take care of. So, and then what happens? Okay, well, for each of these, we always have no matching cell on each of these spots. And then, okay, next line, we're going to do it all over again for these two edges every single time. So that's one optimization we might want to dive in for. You'll notice, though, that there are edge cases. Every time we hit this right-hand edge, we need to check because there might be an existing set of cells over here that are already generated. So this cell group, because it might already exist, we have to worry about that. Same goes for these bottom cells. When we're in the bottom row, we have edge cases down here that will cause us to think twice as well, because once again, there might be another cell group sitting here. So that's one thing we can do, right? That's kind of something obvious that kind of comes off the top of my head. And this is really cool because this is something you might get asked in an interview. Like, this is a cool interview question that I think would stick around really well if I were to ask a new hire something. And since I'm still somewhat going through the interview process, even though I'm mostly done at this point, it's still nice to have this in mind because we can really think of these as something that we can do to simplify our code and clean it up a little bit at the same time. Chakma says, use a sorted array with a log n of n search time. So that might be nice. The one thing to keep in mind for that is that we still have these bad cases. It would help with the bad cases. The sorted array would not need to probably go through every single one, but that's definitely an improvement. So the other thing I was thinking of is that I actually don't know if we have a set structure here, which is kind of frightening. It would be nice if we had a set structure. And what a set structure is set is a data structure. Let's just grab, usually a non-invasive set. You say, oh, I have something like a set of floats, or actually, let's just go even easier, a set of integers, right? And what's going to happen is it's going to create storage space that is dynamic and holds integers in a hash map, essentially. But it's not a key-value hash map the same way you're used to. There's no key-value relationship here. It's all keys. So what happens is when you say, okay, does it contain, 5, it doesn't need to look through the array at each point and say, are you 5? Are you 5? Like, are any of you 5? It just goes, I'm going to hash 5 to whatever array index. So let's say it's just hashed by index. So it's going to go to index 5 and say, is there something here? No? Okay, cool. This is null. And that is extremely fast, right? If we say, yes, there's something in 4, 3, nothing in 2, nothing in 5, nothing in 1, but something in 0, that's extremely fast. Now, the downside of this, sets can only contain unique sets of information. So, for example, we can't have 2 zeros, right? Or we can't have 1 not 1 and 1 1, right? You can only have unique elements or unique hashed elements. in a set. So that's my kind of big thought, is if we have something that's like a set, I would like to swap out, I should stop using the pen as a mouse cursor. If I could have edges and vertices held within a set, I would be much happier, because it would allow me to do fast lookups without changing much of this code. The only thing I would change is I'd rip out this function that does the for loop, and I would just say, no, find this. That's all. So, let's see here. Of course. So, let's see. What kind... oh, gosh, people are answering questions for me. Yes, I'm making a 3D survival RTS. Thank you, Jamin. What's it called? For now, it's called Settlement. That's just a working title. I don't really have a good name. Names are something that kind of come about via gameplay, and I want a good fitting name, and I don't have one quite yet. So we're working on the name. The name will come about as the game nears alpha or beta, probably. We'll see how that goes. So let's see. What do we got? In terms of data structures. Because we have this utility library. An array is nice, but it's not fitting our need. So, auto-release, completable, yada yada. Graph. A directed graph, Hash table, here we go. Rob's minion, yeah, something like that. Just, yes, my minions, go. Alright, so a hash table might be what we're looking for here. If you look, it's got a find function. Searches a hash table for an element having a key that matches the key parameter. Otherwise, that's perfect, right? That's what we're hunting for here. Something like that would be perfect. So if we could make use of this hash table, is there anything else here? Map? Maps are associative, and that's the key value that I was mentioning earlier. And we only have keys here. We don't have values to associate them with, so I'm not too worried about that. Yeah, I'm not really seeing anything else. Static hash. Oh, that's just for string hashing. I'm not worried about that. Yeah. I wonder if this list goes any faster. Is there a find in here? Not really. The only thing it really seems to have is this member function, and even then, that takes a pointer, and we don't have a pointer at this point, so, Alright, let's see here. So, hash table. Type of the class that can be stored in the hash table. Class specified by this parameter should inherit directly from the hash table element class. So this is going to be problematic for our points, and that's kind of a, I might have to think about that. We might have to create some kind of like cell vertex class that is a subclass of point, just so we can inherit off of this hash table element class. Yeah, not the end of the world, just requires a little more work than I initially imagined, which is fine. That's kind of how programming works. You think of something, you go, oh, this will be easy, and then it turns out it's like, oh crap, maybe this isn't as easy as we thought. Yeah, okay, so let's do that with cell edges first. So a cell edge is a, and we need to make this public, otherwise the engine won't realize it's happening. This is a hash table element. There we go. And we need to, let's double check, see if there's anything else we need to attach here. Later, King Elizabeth. Have fun with Total War. Let me know how it is. I've never been a huge fan of the series, but I'm always waiting for the one that kind of changes my mind. So if the new one is the one that does it, I would be happy to know. Must be a subclass of this, that's fine. Upon construction, Yada yada. Okay, class specified by the type template parameter must define a type named keyType and a function named getKey. Okay. The class specified must also define a function named hash, which has one of the following prototypes. Okay. Seems simple enough. So, our cell edge, let's see, keyType. How do we do this? Initialize. Does this function even exist anymore? I don't think it does. Can I pull that out of the header? Initialize. Initialize, you are a silly function that shouldn't exist anymore. Check for insufficient disk space? Really? I've never had a disk space problem. No, I don't. What? I've got 76 gigs free. What are you talking about? Insufficient disk space. Oh, you know what? It's having a problem writing to the database because Very Sleepy is using it. Sorry about that. That's the one downside. Very Sleepy keeps the file open, and because it keeps the file open, when Visual Studio goes to compile your program and create the debug file, it can't, which is a problem, but whatever. Okay, so we've got our cell edge, we've got this hash table element, and what we need to do, we need to define its type stuff, its type information. So we have type def, let's see here, what are we going to type def out for our key type? Because this is going to have a key type associated with it. The question is, what are we going to type def as our key type? Let's say, I don't know how well this is going to work. It really depends on how we're doing this find, I suppose. So the find in pretty much every case is based off the vertices. So we're going to have to come up with a way Let's use a float. Yeah, let's use a float. Let's try this. Get key void const, right? That's what that has to look like. Just double check here. Yeah, I know, it's funny. I say out of disk space, and it does worry me somewhat because I am using a small solid state drive. But at the same time, I'm not too worried about it. Alright, so yes, this matches. The other thing we need is this. We need to write this function out as well. Oh, that's interesting. It has to hash everything down to a 32-bit integer. We might have to figure out how to get to this. Not the end of the world, but I could also look at other things that have been hashed, see how they're used in the hash table in the engine, and then kind of extrapolate that a little bit. Animation headers. So this isn't actually used too terribly often, even in the engine, which is kind of funny. That's fine. That's fine. Take the punches as just roll with them. Fiery mixtape? No. This is no mixtape that you're listening to. This is Monstercat's Twitch channel. Their Twitch FM. I was getting tired of running into people blocking my VODs because of various obvious copyright infringement on music. I don't own any of the licenses for a lot of the music I play. And so because of that, people like to stomp on my VODs here on Twitch and also do the same on YouTube, even though the music is just background noise. How it goes. Okay. So we have to write these two functions out. Da-dum-dum-dum. Let's figure out how to do this. And this has to happen inside of our cell edge function. So here's our cell edge. And we're using the key type. And the key is pretty simple for us. Let's see here. For us, because we want the vertices to be communicative, we want to do something very simple. Now, we're going to have a lot of collisions if we simply add the vertices together, is the problem. So we need something... let's see here. I'm going to pull back paint for a second while I consider this, because I haven't actually fully considered how I would try and hash things. So an edge is 2 points, right? And those 2 points, let's say this is 0, 0, and 1, 0. And then we have 1, 1, and 0, 1. Right? So here's our 4 edges that are not obviously straight, but they're close enough to get the job done. What we need to do, if we just added them together, it wouldn't work. Because this and this, these 2 edges here would be the same, right? If we just said, oh, x plus y, granted, that's partially because we have 0, 0 as an endpoint. What we need to do is figure out how we want this edge here, I guess I shouldn't have this, how this edge here and this edge here are going to be different. Some kind of like spatial partitioning or some kind of like spatial hashing would work. Hash an edge. We have to figure out a good way to do this, because the problem is if we do this in a silly way, the hash won't quite work the way we want it to. You know what? Okay, so one thing I'm adding to the list of, or I'm removing from the list of requirements, we don't have to have it be communicative. So if we have 0, 0 and 1, 1, and 1, 1 and 0, 0, it should be fairly fast for us to generate both hashes, check if both of those exist in the hash map, and that removes a requirement from our list of crazy things we might have to do. So let's take that requirement out. So now we only have to hash 2 points. Doesn't really matter what order they're in, because we can always generate both hashes. So the question is, how do we want to hash this information? Because we can always hash 1 point, right? Hashing a single point is easy. Single point is pretty obvious. You can say, oh, we do x times this crazy y number, or we do some kind of other hashing function that multiplies one, or puts one to the power of the other. That would generate a lot of different numbers that wouldn't collide too terribly often. Let's see here. I'm going to pull up calculator for a moment. Just, let's see. Actually, not calculator. I'm going to use Google. What is 2 to the 16th? That is, right, that's a 16-bit integer, which is 65,000. So, that might work. I think I've got a way to do this that might work. A good hashing function here. Oh gosh. So what I'm reading through right now, people are talking about hashing using prime numbers, and that's not really something that sits well with me. Humble Sapiens, how about an adjacency matrix? I don't particularly see how that would help me. Let's see. This is a concept I've only run into like once in the past, and I don't know if that's the case. Means of representing with vertices or nodes of a graph are adjacent to which other vertices? Another matrix is an incidence matrix. Specifically, the adjacency matrix of a finite graph G on n vertices is the n by n matrix, where the non-diagonal entry is the number of edges from I to j, and the diagonal entry, depending on the convention, is either once or twice the number of edges from the vertex to itself. So here, I'll pull the Wikipedia page over of what Humble Sapiens is suggesting. So the only reason I might not do this is because you'll notice as the size goes up, I would have to create a huge adjacency matrix for something that's not terribly complex. Right? You'll notice all of these have like connections to each other. Technically all of ours are connected to one another. Well, I guess, okay. I see how this is somewhat helpful, but we'd have to create a huge adjacency matrix. Like we're talking, like right now, what? One cell is being broken into a 4x4, I think. Is that what I'm doing? Let's find the code real quick. Where are you? Cell group. Here it is. Cell groups. Side lengths. Okay. So it would help if I need to find a path through the cells later on, but I've already got that information floating around at the end of this process. The only thing that's causing my slow generation right now is the fact that I am looping through far too many times. I'm not really worried about pathfinding. My pathfinding's done. It's just trying a little bit of optimization on this system. Let's see, I'm going to go back to hunting for hash function for two numbers. An int hash, what? Oh, thanks. So we could create CRCs, right? Those are pretty simple things. And that would be nice, actually. Yeah. Let's do that. So a CRC is a cyclical redundancy check. And what these do, let's see if we can find a nice easy CRC in C++. Probably a 32-bit CRC is fine. Yeah, there we go. So what a CRC does is it takes the it takes a number, something like a 32-bit integer, and one bit at a time applies those bits in a function that creates unique or fairly unique enough numbers and essentially generates a checksum out of the bits. But the difference between a checksum and a CRC is that CRCs change based on the order of the bits. So if I say 0101 versus 0110, a checksum might come up with the same value, depending on the checksum you're using. Now granted, it'd be a really shitty checksum if it actually came up with different values for those. But the idea of a CRC is each value that goes in changes a hash, and then you use that hash on the next bit, so that each bit is not just changing the hash, but also cycling through a different hash for each one. It's a very cool thing to see in use. And I would be happy if I could just find one that's already written. Obviously, Boost has its own CRC stuff, but I'm not a huge fan of it. I don't want to include Boost because Boost wants to include a lot of other things. The moment you include one Boost file, it includes a million others. And as far as I know, Boost still doesn't play nice, once again, with the memory manager in the system. Not the end of the world, it's just kind of a pain. CRC32 for a file. Not what I need. Here we go, CRC32 for a buffer. Wow. That looks a little more in depth than what I might need, though. I'll keep it around. Dang it. So apparently there's a CRC in zlib that's actually really nice as well. Let's see here. zlib, do you have what I need? It would be really nice if it did. It'd be really nice if I could just like crack open zlib and be like, alright, there's what I need. Source code, yes please. You'd think something like a CRC would be a fairly simple piece of code, and yet for some reason it's an incredibly difficult thing to crack down on. Okay, let's see. We pulled down the zlib stuff. Let's look through here and see. Holy heck! See if we can. CRC32.h. Cool. Okay. Big fat table. Not the end of the world. Actually, a lot of CRC tables, or a lot of CRC implementations, speed up their systems using giant hash tables like this, and it also allows them to generate systems that avoid collisions a lot better. So even though this looks like a lot of code and a lot of constants to fight with, at the same time, it allows for a much faster generation. This is one of those cases where you are trading off space for performance. Sorry, my brain. So Boost is a little bit crazy in terms of compile time. I'm not too worried about compile time, but I am worried about the amount of time it takes me to make this game. Because as people have said before, and I think Jonathan Blow was the first person I heard say this, you can really optimize your code for three things. You optimize your code for performance, for memory, or for the amount of time it takes the developer to write the code. And I'm trying to optimize for that third one in most cases. This is the one case where I'm trying to swap out that performance for memory, or just for some clever techniques. I'm also trying to swap out some stuff using that. So okay, the H file's pretty empty and meaningless, aside from the fact that, okay, cool, hash tables. Nice. Now the one thing that worries me is I don't know. Okay, it says see the copyright notice in zlib.h. Where are you? The only thing I worry about is the kind of license that zlib is. I don't actually know. Ba-dum. It looks like an MIT-based license, or a simple, like, free-to-use license. I actually don't... There's no name on this license. But it looks like an as-is, and it has full permissions. So, looks like this is something we can use. Okay. This is, possibly a little more crazy than I need to. We might be able to just take some of the like simpler functions in here, rip out the stuff we don't like, or we could just dump it in as is. I mean, it's not like I'm too worried about this. CRC32 little. So the only reason I don't like things like this is that you'll notice they have like all these if defs, if not a, all this stuff defined in here, and I'm not a huge fan of people who do shit like this, who say, oh yeah, we're gonna pound define local as static. Luckily it's in a C file, so in a source file, it's not that bad, but it still, it messes with how I read code at bare minimum. Huh. So is there just a... Okay, I understand what this file does. It's just a little poorly formatted, I guess. So here, let's take these files, include them, and then see if we can twist them into what we need. So, where did I put that? CRC32H and CPP, let's pull those out to our game code. And then we're going to dump them into our game. And they should compile straight up, aside from the obvious thing here that's going to complain a little bit because I haven't filled these functions out. Yeah, let's try and remove some of this stuff, like the make CRCH file. Not necessary. Yeah, let's start with that. Because this is just such a huge, ugly file that I don't like working with it all at once. Specifically, where was it? Make CRCH. Okay. Here we go. Here's the big if def that's in here. And make CRC table, we don't need it because we've already got the CRC table included. Also, this chunk of code here, not necessary. Now, obviously, I've removed something. Oh, I see. So the other thing it likes is this far, and I have no idea what this far pointer is. It says it's included in zlib.h, so I'll probably look at that, decide if I want it. Make. Cool. Can you mix and match C and C++ together? Yeah, you definitely can. C is a, sorry, C is a subset of C++. C++ is simply an extension on top of C that allows for finer control of compiler-defined structures inside C++. I mean, C++ pretty much sits on top of a standard C compiler in a lot of cases. Cannot include zutil.h. Okay, we'll find out what zutil.h has that we want. What do you have? Okay, so far is this weird thing that it wants. Oh Lord, look at how ugly this thing is. If you know, pound define Mac OS X and then some ugly stuff there. This is why. This is why I don't like a lot of third-party libraries. It's just, given enough time, some of these require some crazy pound defines to get working, and I'm just not a fan. So the things that we do need from this, I believe, are this far pointer. Also, you'll see that this includes zlib.h, so the rabbit hole goes deeper, unfortunately. So while I understand, Kodadama, that the portability is actually necessary and helpful in some cases, especially for something like zlib, right? Zlib's a very straightforward kind of library. Ooh, did QISC find something neat that I can just like slap in and be done with? Yes! Oh my gosh. You are my new fan. Or I am your new fan. Other way around. The only worry is, once again, we have to look at license. So this is what QISC linked to. As desired without... Okay, so the copyright says you can use this program or code or tables extracted from it as desired without restrictions. Simplest license ever, right? Yeah, I love it. I love it. Let's do it. Let's just grab this. And even though I've included these files, I'm actually going to just swap over to... Do I really want to dump it in a header file? Yeah, I'm going to dump it in a header file. Be done with it. Unsigned int32. We're going to swap out some of the types here. Yeah, Chokma, I'm searching for a hash function to get a unique hash for vertices and edges also. I think it's c4types.h. There we go. So the only thing I'm going to do to this is I'm going to swap out some types and clean it up. Also, what? P equals buff. Okay. A pointer from the buffer. That should be fine. Well, no. It needs to be... It needs to be type defined. Or type swapped. Doesn't open source already imply a free use license? It does not. A lot of open source licenses are actually, there's a number of things that I have to avoid specifically, and then there are a lot of things I like to avoid as well. For example, things to avoid for any game programmer, there are open source licenses that do not allow commercial use. They say, oh, what is it? I know there's a couple Creative Commons licenses that say no commercial usage. If I ever want to sell this game, I would have to go back, rip out that code, and then swap it out with something else. The other thing to do in some of these cases is that if you look at some open source licenses, they're viral and say, if you include this in a project, your project must also be defined as open source unless you meet this list of requirements, which I am unlikely to meet because I'm using a different kind of engine than most people. So there are a fair number of open source licenses that I have to specifically avoid And it's a little bit frightening that that's the case, but that's kind of how open source licenses have evolved. Let's see here. Let's put some file guards on this, just so we don't shoot ourselves in the foot later, because this is a header file. Cool. That looks good. And I've already removed the CRC C file. Let's just delete that from the system, just so we don't accidentally add it or feel the need to add it. There we go, much better. So we're going to want to hand it a buffer and a size. Simple, easy. I like it. Molto bene. Alright, world generation. Dum-dum-dum-dum-dum. So Chakma is talking about the way in which we're generating terrain and saying we're probably going to limit ourselves to 65k by 65k squares. Is that correct? Let's see. Right now, yeah, we're probably going to be limited by something like that. I mean, that's a huge chunk of terrain, right? 65k cells. It's pretty freaking huge. You can just take a 32-bit integer, put the x index in the low 16 bits and the y index in the high 16 bits. It would be unique, provide additional information about the place of the vertices that a standard hash won't. So the one thing is that, yeah, you're assuming that the vertices have indices, and I don't have that information at the ready every single time. In fact, as we build some of these, keep in mind that we're not just doing this for points, we're also doing this for edges. So edges require a little bit of extra information here, because it's not just a point, but we have a pair of points we have to keep in mind when we're using our setup. Doesn't that make your indexing endian dependent? Would that? It might, yeah. See here. The thing is, as long as you're reading it back correctly, the endianness of the system shouldn't matter too much. Right? Because the reader and writer are going to be on the same system. So when I say, oh, take 4 and put it in these first 16 bits, and then take 4 and put it in the second 16 bits, when you read it back, you're still going to be doing the same left shifting and right shifting to get the two values out of the 32-bit integer. And at that point, things are nice and simple. Is that a better way to do this? Yeah. So I like the idea of using the vertex positions for points, but for edges, when we have 2 points to take care of, I'm still a fan of running it through a CRC function. Or at least running like indices through a CRC function, or something like that. Also, the other thing that I just thought about, because programming is likely one of those problems that has so many different ways you can solve it, it's not even funny. And because I'm doing things in a certain pattern, we could almost abuse the pattern to make this faster. For example, good old paint. All these nice previous ideas we've had, right? Oop, don't save it. I don't want to save this junk. So, oops, that's what I get for holding the pad upside down. So, one thing to keep in mind is that whenever I generate an edge, I go 0, 1, 2, 3, right? So every cell is going to presumably then be attached to because then we would go 4, 5, 6 already generated, and then we go 7, 8, 9 already generated, 10. Huh. And let's say this is a 4x4, just for kicks. So then we go 13, 14, 15. Okay, I'm not seeing a pattern here. I was looking for a pattern. I was looking for some way to abuse this. Oh, also, wait. I messed up my pattern. That might explain why I can't find anything here. So 12, 2 already exists, so we would go 13, 14, 15. And then we go 16, 17. 18, 19. Or even if we could go so far as to pass cells to other cells when we're generating them. Nah. Dumb idea. Don't want to do it. That requires maybe a level of like math that I don't want to deal with. I like the hashing. I think that'll be simple. And I think we can get that done in a fairly short period of time today. So let's go for that. Because we've already got our CRC function. Thank you to Kiwisk for providing that. Because that is something I think I can use. So, okay. Get key. I think we can swap this to unsigned int32 and get away with this pretty easily, in fact. So what we're going to do is at the top of this file we go, actually not top. The naming of the file breaks my convention. Rename. Quick. It's already... What? Oh. There we go. Exclude from project. This is just me being picky. There we go. Pickiness dealt with. Let's see how well that works. Adjust the casing. There we go. Alright, get key. Oh, must return a value. Duh. Return CRC32. Let's see here. Is this namespaced or anything? I don't think so. No, it's not. Okay. Let's look at this. So the only thing that's catching me off guard is the fact that this starts with a CRC int32. I'm not sure if... What is that sucker used for? Let's look at the definition. Okay, it's just the starting offset. Interesting. Star Trek fans in here will understand me. Or I hope they will. Vertices 0. Actually, we can just say vertices, and then size would be 8. So the only thing is that this is a .2D pointer, and I don't like that. I don't want to be hashing pointers. I want to be hashing actual points. So what we're going to actually hash, let's see here, vertices 0.x, normalize. Is there like a hash function in here? Of course there isn't. Of course there isn't. Rotate, no. Alright. Oh, okay, here we go. Float is incompatible with a constant. Oh. Yeah. Tenanet gets it. No. It is arrow X. It's just, what I need to do is hand it the address for this. And right now this is only hashing the X value in. I don't want to just hash the X value. So my only worry at this point, my only worry, is that I'm going to end up with some floating point difference between the values. And that's going to kind of shoot me in the foot. Oh well, we're doing it. That's how we're doing it. So, we're going to start and say int CRC. We'll start with 1701 as a perfectly valid offset. We'll go from 0 to 2. We are going to say the CRC is equal to CRC32, that includes the CRC, contains verts 0, x, and its size is 4, because that's, 32-bit, 4 bytes, right? And then we're going to do it again for y. We're going to swap this from 0 to I. And this should do the trick. Return the CRC. And when we hash a CRC as well, we could actually just do the same thing. Oh, I see. Okay, I see what they're doing. So we have to provide a get key, and we have to provide a hash for that get key. Now I understand what I'm doing here. Okay, so when we say get key, what we actually need to do is return vertices. Cannot convert from .2D to key type. It's still having trouble converting between that and the key type. I'm missing something here. Cannot convert from a .2D pointer const array of size 2 to a cell edge key type, where the key type is, oh, Oh, come on. Stop complaining. What's wrong? Syntax error. Oh, derp. Haha, don't mind me. It's a pointer to an array. The only thing that I... Why is it still complaining then? Vertices. This should be a point2D double pointer. Let's swap this out at bare minimum, right? Does not match the function type. Conversion loses qualifiers. Because the double pointer needs to be constant. Really? I guess... Does it really? Still complaining. I think... It's something like this. There we go. So the reason you have to fit the const between the pointers is because when we're handing off the key type from one to another, one of these is a, because it's a pointer, let's see, how do I explain this? Because it's a pointer 2D pointer, a point 2D pointer, there we go, I said the words right. Because point 2D pointer is our standard type, that's what we're passing around. Those aren't constant. What is constant, and what has to stay constant, because the getKey function is constant, is this second pointer here, which is the pointer to the array of point2D pointers. That's why we have to fit it into that spot. And that's why it now builds happily. Right? Yes. Good. Okay. So, our cell edges can now be hashed. Great. We need to swap the cell, let's see here, not the cell group, don't care about cell group, cell system, a map of cell groups, fine, whatever, don't care, an array of cell edge pointers, no, this is now a hash table. Oh, and because it's... edge array, even though it's now a hash table. Initial bucket count. I actually have no idea what my initial bucket count should be. Let's see here. 0 and... let's say... I don't know. How many edges are going to be in this sucker, right? A 4x4 is going to be pretty huge. There we go. That should generate enough for us. And then max average depth. I have to look up the documentation again to understand what the heck is going on here. And I can close this adjacency matrix stuff. The number of buckets initially used by the hash table must be a power of 2. Okay. Because it has to be a power of 2, I'm going to assume there are going to be a lot of these. So 256 sounds fine. The maximum average size of each bucket allowed before the hash table is expanded. Ah, okay. Maybe this doesn't need to be quite so large. Let's see here. So 16 and 4 edges. Yeah, 64 is a good size. And the what is that? What did it say again? It was the max average size of each bucket allowed before the hash table is expanded. Hmm. I'm going to find something else that is used and just look at their usages just to see what's going on here. Hash table of resource bases. It uses 16 and 4. Let's go for 64 and 16. We'll see how that goes. We'll see if this ends up needing to be modified in the future. But this alone should fix up a lot of stuff. Oh, now we need to, of course, modify a lot of stuff. Anything that took... we're going to change this to the edge hash, firstly. Actually, yeah, edge hash. Everything that took that cell edge list before, hash table of cell edges. In fact, I'm just going to grab this whole thing. Cell edge pointers. Get cell edge. You are past this object. Or you're past at least a reference to this object. In fact, it would probably be faster to just do an array of cell edge. Cool. Now we have to modify everything out here. Let's see here. You can use an array. Find valid lower neighbors. Interesting. I'll have to look at that one later. Oh, actually, I may not wish to switch that function over. Is that? No. We still have a couple things. Okay, so this find edge by vertices function, this is now actually... Let's see here. We get a point 2D, we get another point 2D. And what we're going to do is we're going to generate both hashes, and then using those hashes, we should, let's see, should be able to do this. Cell edge hash how do we do this? Point 2D pointer array, we're going to call it vertices, 2 equals v1 and v2. Why are you complaining? Oh, because you guys are constant. That's fine. Whatever. So, we're going to pass it vertices. And we're going to say unsigned int32 hash 0 hash something. Hash 1, I guess. Hash vertices is incompatible with... Really? Oh. Interesting. Const double pointer is incompatible with type. One would think that we'd also make the hash function constant as well. Cell group, no. Cell edge. Here you are. Oh, sorry, cell edge. My bad. It's interesting that this doesn't promise to not change. Although it looks like we can do that just fine. There we go. So we have a few other things. Obviously, this won't work anymore. What we're going to do is we're going to say, okay, hash1 and hash2. Or actually, we should probably do this unsigned int 32 hashes. So it may look like I'm duplicating for no good reason, but what I'm actually planning on doing here is we say vertices equals v2 and v1. Just in case the vertices end up in different orders. Too many initializer values. What? Grumble, grumble, grumble. There's a way to do this. Will that work? And then we say vertices 0. Yeah, that works. Cool. Vertices 1. Or I guess more specifically for int I equals 0, I is less than 2, plus plus I. Unsigned int 32 hash is going to be equal to this, where 0 is actually I. And once we have our hash, we're going to say, does the edge list contain? Now, granted, the question is find hash. Or, I guess, find vertices I. Okay. And this should cell edge pointer. Edge is this. Then we say, if the edge is not a null pointer, we return the edge. There we go. Much better. Much simpler. I like it. Now we've got some places where obviously things are still not quite happy and we need to clean that up. Insert. Done. Let's see, how many errors are we down to? Or how many do we have left? Not telling me. Okay, fair number. Interesting. I do some silly things in here. Granted, this will clean some stuff up as well, so that makes me happy. E equals a new cell edge with the following data. Come on, I told you copy. Now I tell you paste. There we go. So we're going to tell it insert E, and that should be that. Don't know why I was doing that silly stuff before. You are not an array. You are a hash table of cell edges. I'm leaving the names as is for now because I can always go back and clean up names later. Is not a non-static. Oh, because I named it. I named its change. Changed its name. Words, Rob. Edge hash. Edge array is an undeclared identifier. We're actually changing that there. Cool. And maybe, just so, for the sake of consistency, current document, every place that says edge array, we're going to swap it out with edge hash. Just for my sanity. Oh, except for U3, because U3 actually are edge arrays. Okay. Okay, moment of truth, right? Guys? Why is it taking forever? Like, really forever. Not just like a little forever, like this is going. Why? So it looks like we already broke skirts with this code, right? All the skirts are just straight up gone. Also, that didn't seem like it was going much faster. In fact, it seemed quite the opposite. Okay, let's see here. Let's run Very Sleepy again. Part of me is curious, and part of me also wants to know why skirts broke when I did that. Honestly, skirts shouldn't be breaking. At least as far as I can tell. Cell system, cell group. Let's see. Let's look at the generate mesh function before we run Very Sleepy once more, just to make sure that we're doing this right. As far as I know, though, I don't actually use edges in this system. Let's see here. We allocate based on vertex and triangle count. That's... And then we use skirts to check. Ooh. Go to definition. Okay. New cell. Not group, just new cell. Okay, I'm gonna dump a breakpoint here. Before it took about 3 seconds to generate, 2 to 3. Now it's taking like 10. So this is not changed, right? That's simple as before. This... So we've got these 2 sets of vertices, and these are going to be what find us our edge or not. So that's null, and the other one's null. Do we... Okay, question number 1. Do we ever find edges based on the system? No, it doesn't look like we do. Ever. So that's problem number 1 I'm noticing. Is that... Why aren't... Okay, well I guess we can look into the hashing functions, right? That should tell us what's going on. So, first cell gets generated. Here is our first edge getting generated. Now we create a new cell edge. And when we insert that new cell edge, what it's going to do is it then... Let's see. It gets the key, which is that vertex... This, right? And that's -10 and minus... Okay. And we use the hash function that we have. So our CRC becomes this kind of meaningless number to us, right? -156817346 And that's fine. We kind of expect... Oh! I say I expect that, but this should actually be an unsigned int32. So that might have been an issue. I don't think it's going to be the issue. But let's see. Specifically, this function here. Yeah. So it's generating so many more edges because of this, it's not even funny. Okay, first things first. To make this simple and easy for us to debug, we have to cut down the number of vertices flying around. Otherwise, there's just too many for us to handle. So, specifically, in the world generator, we're going to hunt down the terrain generator, tell the terrain its size is 1, and its builder is a resolution of 1. Right? Nice and simple. Even though this is quick, this is a good test case. It's also hilarious to watch the trees fall through the map to infinity, but whatever. Oh, and that's why it breaks the skirts, right? Each time it looks at a skirt and it says, oh, who's your match? Like, do you have 2 cells attached to you? And because every single cell has its own copy of the skirt, then we're duplicating all this data, and every skirt thinks it's the one side of an edge, and that there's nobody on the other side, so no skirts get generated. Ta-da! Okay, so logic tells us that if we fix one bug, the other will get fixed. Great. So I'm actually going to go back to Paint for this. Just for the documentation of numbers, so you guys can see what I kind of do when I get around to debugging stuff like this. Because this is unfortunately something that's going to require a little bit... Can I draw straighter lines? Close enough, I guess. 1, 2, 1 through the middle. Cool. So, what we're going to do... Yeah. We say load world, and it says, okay, I'm inserting a vertex at -1, and we are going until, so we're going from 0, 0 to -1, -1. So I think that's this one here. So if this is 0, 0, this is -1, -1. It's creating an edge. One of the 4 edges, specifically. I think this is it goes top edge first. So we're going to... I have a drawing tablet, and I've gotten used to using the drawing tablet as a 2726. I've gotten pretty used to using the tablet as an actual mouse pointer too. 2726 7. No, actually, we don't even care about this one. Why am I writing this one down? This one doesn't matter. This one doesn't matter. All these outside edges don't matter. It's specifically the edge between, and let's just double check that this is an edge we care about. This is the edge that goes from -1, 0 to 0, 0. Okay, so this is actually an edge we care about. I'm just going to hit F10 once so I have the hash. So it's this one here. So this one's hash 2726 7938 793. Oh god, these are long. Brain. 2726 7938. I want to make sure I get this right. 7938. I think the next number is a 1. 93831. 93831. And that's this one right here. Alright, so we've got our one number that we care about. So I'm just going to F5 around until we see, and actually I should pull up a watch probably so that I can find what I'm hunting for. Specifically E, let's see here, E vertices. And there we go. This should tell us what we're hunting for. So when we see one that's going from -1, 0 to 0, 0, that's what we're hunting for. So there shouldn't be a ton of these. -1, 0 to 0, 0. Here we go. Okay. So it couldn't find the existing one. So my curiosity is piqued here. We get the key. And the key, sure enough, says 0, 0. And let's look at the element. Actually, the element is a better... There's 0, 0. There's -1, 0. And that's our same value. And it hashes... Oh, to the same value. So why didn't the find function find it? That's my question. Interesting. Okay, so it looks like those two are coming back just fine, which is the most bizarre. Even though we have created these vertices, for some reason, actually, let's go through and make sure we've got the right set again, just to make sure. So here's our -1, 0 and 0, 0, right? So it's our point. So here's -1, 0, and here's 0, 0. So it's this edge, right? There's no mistaking it. We are staring at this. There we go. Nice red line. Make this really stupidly obvious for us. I can't. I'm not doing well enough covering up the black line. Okay. So when we say insert, and I got this hash right, 2726, yes, 793831, yes, okay, hash is correct. We have double checked it. So, where is the find function inside hash table? That's my curiosity. So when we say find, let's see here. Vertices I and this. So we're going to look at these and wait for that right number to come around again. Not quite. Nope. Let's delete this just to make sure we got this. Nope, not quite. Never mind. 0 and 1, no. Okay, here we go. 0, 0 and -1, 0. This should... We've got our 2 pointers in order. So we call find on... Which one is this first? This is the one that goes with 0, 0 first. So this one should generate a bad hash that we don't really care for. 27267933831. So actually, this generated the same hash. Suddenly I'm worrying a little bit. It gets a bucket. find... Is there a way to check? I mean, here's the hash value for the bucket. We grab the first element in the bucket. How many elements are in this bucket? That's my curiosity. And then it says if one key... Okay, then it's checking... Oh, gosh. So it's checking actual keys at that point. We're never going to win if that's the case. Because what it's doing is it says your hashes are the same, and it proceeds to double check by not just taking the hash at its face value, but because he assumes that there might be some overlap in hashes, it then proceeds to check the keys against each other. And because, even though the hashes check out, if you look at the code we're using to generate these values, back up all the way out, this is a pointer, right? This pointer is never going to match the code that is inside the other... It's never going to match. It just isn't. This hash map is... Oh gosh, it's a complete pain in the ass. You would think I should be able to just jump in and say, oh, well, you know, because, yeah, because the hashes match, we should be fine, but for some reason, it feels the need to also check, and I'm just going to walk through the rest of this just for my own sanity's sake. It's also finding multiple elements with the same hash, and that's somewhat worrisome as well. Get some rest. It's, I don't know, I haven't been missing too much sleep lately. Have I? That's always a good question. Whose idea was this? Yeah, that's a question you definitely never want to hear in a meeting. It's just like, don't mind me. Gosh, so it's this line right here that's really sticking me. Because I'm using pointers for a lot of my hash generation, and because my hash generation is